about quantum fields in the Schwarzschild geometry. And today I'll talk about the version of the geometry where there's a collapsing shell. Then I'll introduce the black hole information problem, and say a little bit about why probably most people now think they know what the resolution is. And then I'll the resolution being that the evaporation is unitary. And then I'll talk about some consequences of the idea that the evaporation is unitary. And we'll see how far we get. Okay, so as I've written now several times on the board, so now I'm going to start studying the free quantum field theory in the Schwarzschild geometry. So far I was just sort of making general comments. Near the horizon it looks like Rindler space, this kind of thing. But now I'm actually going to talk about the free field. So as you'll remember from before, whenever I have a free field, the thing that you want to do is expand it in terms of some set of modes, f sub n, which are solutions of the scalar equation of motion. So when I was talking about the free field in Minkowski space, the equation of motion that these guys were solving was the scalar equation of motion in flat space. But now we're not in flat space, we're in the black hole geometry. So the equation looks a little bit different. What it looks like is you take 1 over the square root of minus the determinant of the metric, where, as you may remember, the metric, these g mu nu, this is just a matrix where the metric is defined like that. And then so this is how you can find g mu nu from the way that Rob and I have been actually writing metrics. Then the equation of motion is like that. Okay. So you can see without too much trouble, so if I picked a g mu nu to just be minus 1, 1, 1, 1, then these derivatives would pass through the metric and just be contracted here. These would cancel, and we'd just get back to the usual wave equation in flat space. So, but this is the correct generalization to curved space-time. So then we want to find these modes Fn that solve this equation, and just sort of look at what their structure is. And I want to emphasize this may look like a technical problem, but so I said yesterday that 4/5 of understanding black holes is understanding the Rindler decomposition, and maybe another tenth of it, I'd maybe even say more, is understanding the structure of these modes. So it's worth sort of working it out carefully. Okay, so what are we going to do? So as usual, it's convenient to go to modes of definite frequency, where now here the time here is the Schwarzschild time, the first time I wrote down that in the lectures. Now there's spherical symmetry. So maybe I'll write the metric just so that we have it. Right, so now this is this time, and then, okay, there's spherical symmetry, so every physicist knows what to do when you have spherical symmetry is you expand in spherical harmonics, which are just some complete basis of functions on the two-sphere. And then, S in Rindler space, there will be some radial wave function type, wave function looking thing, psi, where now I've pulled out this factor of 1 over r for convenience. So now you can plug this into this, and in doing so, it's very convenient, again, to introduce the tortoise coordinate, which I've used several times now, so it doesn't count as a new coordinate. And then you find that, again, this psi obeys one of these Schrodinger type equations. So So here the equation is d squared dr star squared psi plus, so I guess it's psi omega L, plus v of r, where I'll tell you what that is in a second, equals omega squared. So this is, again, the Schrodinger equation. But of course, I have to tell you what v is. So what's v? V okay, so it's some function. And then, as is usual here, whenever I write an r, I mean that you solve this equation to determine r in terms of r star, and then now this is a well-defined, differential equation.
At W and N is indicating F for N?
Yeah, so this N is labeling all of the modes, and so just it's a sort of catch-all thing, so I can write a simple equation, and then and then in the particular context of Schwarzschild, I'm breaking up N into these three indices. Okay, so this is actually, there's a lot of physics to be enjoyed from this expression for the potential. So let's say, let me first, make some comments about the mass here. So I'm about to dispense with the mass, but I just want to first say something about it. So if r is large, then you see that this approaches a constant, because this falls like 1 over r squared at large r, which is canceled by this r squared, and everything else is subleading. So this potential approaches a constant at large r, which means that there won't be propagating solutions, solutions which oscillate out at infinity, unless if m is non-zero, unless omega is greater than or equal to m. Okay. So that gives you propagation. Now, I have to tell you what kind of omegas I'm interested in, but as you may remember from the last lecture, we found that there's some temperature for the black hole, which is of order 1, because remember here so this 1 here says that I'm still working in the convention that 2gm equals 1, the Schwarzschild radius is 1. So then the temperature is order 1 in these units. I'm going to be interested in omegas which are of order the temperature, because those are going to be the ones that are going to be excited in the thermal distribution. They're going to be the ones that are interesting. And then the point is just that, so what does that mean? Well, it means that the mass of the black hole is sort of, it's either going to be much larger or much smaller than the temperature typically, so because, the temperatures of black holes that we care about are quite small. So if the mass is much larger than the temperature, then it means that the modes are just going to be they're going to be exponentially decaying away from the black hole. They're going to be just confined to be very near the black hole, and they're not going to be so interesting for us. On the other hand, if the mass is much less than the temperature, then we can just set it to 0. So indeed, that's what I'm going to do. And so I'm going to be slightly less general by doing that, but I think it's a well-motivated generalization. So I'm going to get rid of this term. Okay. So in the massless case, so let's get a better sense of what this is actually doing. So in terms of the tortoise coordinate, the r star. So remember, r star is running from minus infinity to infinity. At large values, it's just proportional to r. And then so we can look and see what's going on here. Well, so say L is not 0, then the potential is falling like 1 over r star squared. And if L is 0, it's falling like 1 over r star cubed. So in general, it's falling like some power at large r star and approaching 0. Now, as r star goes to minus infinity, then I can ignore this term. So then what's happening is that r is like e to the r star, okay? Or actually, it's it's so for r star much less, let's say going to minus infinity, that's what I should have written yesterday, then we have that r equals e to the, let's call it r minus 1 equals e to the r star, okay? So the relationship is exponential. So now notice that as r star goes to minus infinity or r goes to 1, this vanishes. Okay, the potential again goes to 0. But now it goes to 0 exponentially in terms of r star because of this. So then what happens is there will be some barrier, and then it'll rapidly decay to 0. Okay. So that's the basic form of this potential. So whenever you see this kind of potential in quantum mechanics, what you always say is, oh, this is a scattering problem. So, you know, the modes come in from here, bounce off and go there, and some is transmitted. Or you can say modes come in from here, some is reflected, some is transmitted. Now, we'd actually like to get a sense of how much is transmitted, say, as a function of L. So to do that, you can just observe that it's interesting to look at the sort of large L limit of the potential, just so we can get sort of some idea of, you know, does the peak move around? How tall is it? This kind of thing. So, and it's fairly easy to see that if L is much greater than 1, where I mean much greater could be like 5. I mean, it doesn't need to be that much larger. Then the peak, R peak, is 3/2. Okay, you can turn that into the tortoise, and it's some messy thing involving log of 3/2, but I'll just say it in terms of r. So the peak is at r equals 3/2 for all L. For all L much greater than 1, and then V of r peak is of order L squared. Okay, and that's fairly obvious. I mean, there's an L squared here, so clearly in the L squared limit, you evaluate this at 3/2, and then this is just going to grow like L squared. So what does this mean? So first of all, so it means that there are modes in here. So incidentally, the exponential here, that's the exponential we found in Rindler space before. Remember in Rindler, we also wrote down an effective Schrodinger equation, and this potential, the potential just grew exponentially forever. So the thing that's new in the black hole is that eventually you get to the edge of the sort of near black hole region, and then the potential turns over and goes back to 0. Okay, and that's very interesting because it means that you got modes here which look like they're confined, and often the modes that are confined here are called the sort of the thermal atmosphere, or now in the literature people have started calling this region the zone. Very charming, but the confinement isn't perfect. For all of the modes, there's some tail where it decays exponentially through here and then starts oscillating again out at infinity. And that's the sort of essential thing, actually, for Hawking radiation, is that this ability to tunnel through and then continue propagating is what allows stuff to get out of the black hole. Now, because the height of the barrier grows like L squared, it means that the tunneling, the transmission coefficient for coming in from this side is getting smaller and smaller as L is getting larger. So the modes that have the easiest time making it out through the potential are the lowest L modes. Say L equals 0, maybe some L equals 1, but not much more.
How can we identify the particle? So if you expand it that way.
Yeah, good. So that's just the usual thing about quantum field theory, right? So you write down these modes, and then the coefficients of the modes in the expression of the field are creation and annihilation operators for particles in those modes. So, and then your intuition should just be that sort of wherever the non-trivial support is of the modes is where you're most likely to find the particles that are created by the creation operators for those modes. So, these modes here that oscillate here and then have some tiny tail and then oscillate some more here, you can sort of think of them as sort of mostly being here, but then having some tail that sticks out here. Now, actually, there's the usual subtlety that these aren't normalizable because they're plane waves, so you have to make wave packets, and then, once you make wave packets, then what I said is unambiguous. Yeah?
Sorry, could why we are ignoring m squared term?
Oh, yeah. The argument was just that. So if you think think about like an electron or something, then the mass of the electron is actually much larger than the temperature of a typical black hole. So then we argue that heuristically, and I'm going to argue more carefully now, that there's some Boltzmann distribution. That the black hole is in some sense a finite temperature object. But this E is the relativistic E, which means that it's something like m squared plus k squared. So if you have a particle whose mass is bigger than the temperature, then the probability of finding that particle is exponentially small. So the modes corresponding to the guys with mass are just not very populated in the states that we're interested in, because the states we're interested in look thermal with this temperature.
In some sense, we are looking at only small black holes.
Well, no. So bigger black holes have lower temperature, because remember ignoring everything but the mass, the temperature is like that. So the larger the black hole, the lower the temperature. Yeah, I mean, there is definitely some crossover region where for any given particle, there's some particular mass of black hole where you're at the crossover point, and I'm choosing to neglect treating that just because, time is finite. But most of the time, the particle will either be much heavier or much lighter than the temperature. So then much heavier is boring, so then I'm going to do much lighter and just set the mass to be 0. Yeah?
Just to make sure that I understand right, what we are looking at now is all outside the Schwarzschild radius, right?
Yes, that's correct.
So when you said that something can escape the black hole, you meant not from really inside, but from...
Yeah, from the outside. Good, that's correct. Yeah, absolutely. I should have said that clearly. So the horizon is at r star equals minus infinity. So you can escape from the black hole, but you can escape from this barrier. Yeah. Okay.
So when you consider the case L equals 0, you have some weird effect, right? That the sign of the potential changes when you process r equals 1.
Oh yeah, but that's true. But you should just think. I mean, I'm not studying the region where r is less than 1, because I switched to these tortoise coordinates where r equals 1 is at minus infinity. So I'm just trying to describe what's going on outside of the horizon. Yeah, that was the point that was being made here too. Yeah.
So the difference with Windler was that in Windler only this accelerating observer could see.
Yeah.
The one in the infinity couldn't see. And here is the mechanism why you
Yeah. So this is why. It's because this barrier turns back over and goes to 0. So then you can you're just sitting there again. Yeah. Yeah.
So that barrier actually seems purely quantum mechanical.
No, it's actually not, because if I'm sure at some point in your life you solved the geodesic equation for a massive or massless particle in the Schwarzschild geometry. So, and you found that there was some effective potential where you were, so if you have some angular momentum, then there's some kind of barrier. So that actually comes from this. In the limit where you take, the wavelengths of the particles to be short compared to the Schwarzschild radius, that's sort of the classical limit.
So what happens classically at r equals 3
So yeah, that's the smallest stable circular orbit, I think. Yeah.
That may be a similar question. What makes the high angular momentum state be more confined? Usually it's the opposite, right? Usually it's easier to escape when you have
yeah, it's a centrifugal barrier, right? And the centrifugal barrier gets higher. So I'm not sure what to say. I don't know if I can give a completely intuitive explanation of that, but I mean this reduces to the usual Newtonian calculation. Yeah.
I mean, if you're coming from the outside, it's the barrier that he's used to, and that's the first term. The
Yeah.
-1 is saying the nonlinearity in gravity, which turns it over.
That's right. Yeah. So yeah. Right. The fact that it comes back down is general relativity. So in Newtonian physics, it just keeps going up. That's right. Yeah. Okay. All right. So moving on. Yeah. So yeah, in general, we should really think of this as dividing the modes of the black hole into being isolated in two different interesting regions. There's the region out at asymptotic infinity, which is sort of the modes that are just flying around far from the black hole. And then there's the modes which are confined to be near the horizon. Now, of course, this distinction only makes sense when the temperature is small, or smaller than the height of the barrier. And so we see that's basically going to be true here for, when the energy is smaller than the height of the barrier, which is true for modes whose energy is of order the temperature. And those are the only ones where this distinction really makes sense. And if you think about it for a second, this is obvious. Because if I jump into the black hole, I'm not going to bounce off of the barrier. I'm going to fall in. Okay? So why is that from the point of view of this? It's because the frequency of me and my particles is much higher than the temperature of a black hole. Okay? Assuming that that my size is smaller than the size of the black hole. So then I just will coast over the barrier and fall in. But this distinction is very important in thinking about the information problem in firewalls. For the guys whose frequencies are below the height of the barrier. Okay. So now let's try and I want to now, from the point of view of the Penrose diagram, try and interpret what this scattering problem is saying. So what's going on? Well. So the whole diagram is like this. So far we haven't put in the infalling shell yet, and we're just looking in this region. Okay. So in this region there's a J minus here, there's a J plus here, and then there's a sort of black hole horizon here, and what's called the white hole horizon here. So then if you look at this potential, right, so let's figure out what everything means. So say I've got a mode which is going in this way from the left. Then from this point of view, that's a mode which is propagating in from the white hole horizon. Okay. Similarly, say I've got a mode which is going that way. That's a mode which is going out through the black hole horizon. Okay. And then the barrier, it's at some fixed r. So as you may or may not remember, lines of fixed r sort of look like that. So the barrier is something like that in the Penrose diagram. And then similarly, so we can look out here. So we can have a mode, coming in from here. So that's like us trying to jump into the black hole. And that's coming in from J minus. So now remember, I set the mass to 0. So massless particles come from J minus and not from I minus. And then, you guessed it, if you've got a mode that's coming out that way, then it's a mode that's going out at infinity through J plus. Okay, and then so what we're doing here is we're sort of studying the scattering problem in that diamond. Okay, now to figure out. So far I haven't actually said anything about the quantum state. I've just been talking about the modes that appear in the expression of the field operator. But to actually figure out what's going on, I need to give some prescription for the quantum state. So in this global geometry, there's a natural prescription. It comes actually from looking at the Euclidean version of the Schwarzschild geometry. And I think given the speed that things are going at, I'm not going to try and get into that today. But you can sort of guess what the answer is just from Rindler space. So what it says, so remember in Rindler space we found that the things on this side were entangled with their CPT conjugates on this side. Okay? And well, what does that actually mean? It means that we should think of the wave function as just mode by mode. So I take a product over. Okay, now I'll not try and normalize it. And then for each mode, let's see, how do I want to say this? So we've got the number of particles in the omega LM mode on the left side, the same number of particles in the omega LM mode on the right side, except that technically I have to do CPT, which I think puts a minus in front of M here. And then we get this Boltzmann kind of factor. So n times omega divided by 2 times the Schwarzschild, times the Hawking temperature. Okay? And this is the state. This is the quantum state that we're interested in. I guess I didn't actually write it out for Rindler space in the case of the free theory. In the Rindler case, I just wrote it out in terms of boost eigenstates. But here, those the boost eigenstates become these modes exactly that we're talking about because I chose them to have definite Schwarzschild time. And we saw yesterday that Schwarzschild time is the thing that turns into the boost energy near the horizon. Now, that's not really a derivation. To really derive it, I have to talk about the Euclidean geometry. But I think it's at least a motivation for it. Okay. So this is the state. N? Yeah, so M. M is the other label on the spherical harmonic here. So it's just along for the ride. It has nothing to do with the mass. I'm sorry. Yeah. That was a clash that there's absolutely nothing I could do about just because both notations are 100% standard. Yeah. The mass never appears as an index, though, so that's a helpful... Okay. So intuitively, what does this mean? Okay. It means that we've got a thermal bath of modes going in, excited here. So we've got the same here. Okay. We've got a thermal bath going in from both sides. We've got a thermal bath going out from both sides, and somehow the whole thing is in equilibrium. So the wormhole is sort of absorbing energy and emitting it at the same rate in such a way that the energy and temperature of the whole thing is constant. Okay. So that really is the physics of the two-sided black hole once you include quantum fields. All right. So if there aren't more questions, I'll go on to the one-sided collapsed black hole. But first, okay. Yeah. Yeah.
So if you move the black hole forward, that's not.
Oh, I see.
So these incoming and outgoing particles on this picture of the B,
Yeah.
they go from the right and scatter back. How
Yeah.
do you look on the picture with the potential? These arrows that you broke,
Those?
where are they? Yeah, where are they?
Yeah. So yeah, in the notes I did this with color to try and make it clear. Maybe
Arrow from this picture.
on here. Yeah, I'm gonna try and do that. So if blue
And then it scatters back, yeah?
and blue, so that's like this, and then this one green here is like that. Yeah, and then on the other side, that's these ones. So this blue here is that. By using the same color, I may be making it more confusing, but. Oh, so yeah. So remember, so this picture only applies in this wedge. So I've pulled a bit of a fast one on you at the end, which is that I then did this whole analysis again in this wedge, without telling you, and then I used the fact that the modes on this side are entangled with their partners on this side.
Where is the tunneling?
Well, the tunneling is here, right? You see, because it's tunneling from the point of view of the effective Schrodinger problem that I studied for the modes.
So this means that some modes going from the left can tunnel to the right.
Yes, that's right. And modes from the right can tunnel to the left.
So here in this picture, everything is possible.
Everything is possible. Yeah, that's right. So there's flux coming in from infinity, because we're feeding the wormhole. We're sending in thermal excitations from here, and then some of them are bouncing off of the barrier and going back out. Some of them are transmitting through the barrier and going in. There's actually some flux coming from here, and then some of it bounces back and some of it goes through. So everything is happening.
For an ordinary kind of Schrodinger equation, you would have two solutions. One is like from left to right, and the other is from right to left.
Yeah, good, yeah, yeah. So, and those are the kind of those are the, I forgot to say that explicitly. Those are the two kind of, the modes that are in the different regions here. So if you imagine the modes where you start from this side and reflect, so then you've set the coefficient of this to 0 for that kind of mode. And those are the modes that are confined in the zone, okay? The other kind is the kind where you set this to 0, and then you go here, reflect, and have some transmission. And those are the modes that are sort of, have most of their support in this region. Yeah, so good. That's a good point. So what I meant by that was that both are excited equally. Yeah, I should have said that more explicitly. And that's going to be important actually in when I do the collapse geometry now. Yeah.
Can you repeat why you said, what was the reason why you said that there's an equilibrium between the two sides of the black hole? You said that there's like as much energy coming from one side to the other or something like that?
Oh, yeah. It's all I really meant was that the flux in here is the same as the flux out here, and the flux in here is the same as the flux out there. So, yeah. Stuff is not passing from here to here. Yeah, that's right. Okay. So now let's talk about the black hole that you get from a collapsing shell, the real black hole. So maybe I'll make the shell in red. Okay, so I made the black hole out of some photons. So now, so I can still try and, so morally I still want to do the same thing. I want to look for solutions of the wave equation in this geometry. But the solutions that I just spent 20 minutes or whatever describing are only correct up here, okay? Because above the red line, this is the Schwarzschild geometry. So the solutions I just described are sort of valid in this region only, okay? Then down here, we've got Minkowski space because the shell hasn't arrived yet. So then there will be so the solutions here will just be empty Minkowski solutions. So for example, they could be plane waves, okay? And then here, there's going to be some matching where we have to sew together to get the full solution. We have to take the solution up here, match it across the infalling shell to a solution here, and then that whole thing will be one of the modes that appears in the field. So, in particular, a crucial point is that the presence of the shell breaks the time translation symmetry of the geometry. So in this metric, if I take t and I send it to t plus a constant, I get the same geometry back, okay? And the fact that I have that symmetry is what allowed me to find solutions of the equation where you just have e to the minus I omega t out in front, and you can just pull out the t dependence. But once this shell is here, I'm not going to be able to do that anymore. Now it's true there is a time translation symmetry down here that's just the ordinary Minkowski times translation symmetry, but it doesn't match smoothly onto the Schwarzschild symmetry, which is doing something like that. So as you go across here, you can get a mismatch, right? You can take a solution which up here in the Schwarzschild region looks like e to the minus omega t. Maybe I'll write Schwarzschild. You pass it through here, and once you've passed through here, you'll find that now the solution down here will have components that involve other frequencies, not just the frequency that you started with, because you didn't have energy conservation going through the shell. And in particular, down here, you can get both positive and negative frequencies to come out of this, okay? Now, what does that mean? Well, among other things, I guess I wasn't extremely explicit about it before, but when I wrote down this decomposition of the field, you could have asked me, well, how did I decide which operators are creation operators and which ones are annihilation operators? You might say, well, why didn't I just call Fn star Fn? Okay. Well, and the motivation I had in mind was that when I wrote this equation, I guess I didn't say it explicitly, but I was assuming that omega was positive, okay? And then the definition is that the coefficient of e to the minus I omega t is an annihilation operator, and the coefficient of e to the plus I omega t is a creation operator, okay? Now, for some, it's by now I'm used to saying it, but this kind of mode people usually call positive frequency when it's minus I omega t.
It should be relative to the IKX, I mean, the free.
Well, yeah, so not actually not, right? Because the momentum can be going in either direction. So the thing that's important is that it is positive or negative energy, and that's this sign. So. Yeah, that's right. Yeah, that's right. Yes, as we learned from Frank. Where's Frank? Yesterday, we would do e to the minus I ht, and that's evolving forwards in time, and that's what this is. That's right. Yeah, that's right. That's right. Yeah, I mean, I think it's correct to call it positive energy. It is just a little bit, when you write it down, it looks a little funny. Okay, so then the statement here that a solution which starts out positive frequency, well, now you know what I mean, that it now mixes with both positive and negative frequency, means that if I expand this field in terms of creation and annihilation operators for the modes that are simple here, then they'll get mixed up with the creation and annihilation operators for modes down here, because modes which are positive frequency in one region involve both positive and negative frequency in the other region. Okay, so now that has interesting consequences because say that for example I wanted to define the ground state here, say omega, as being a state which is annihilated by all the k's in the Minkowski region, all the lowering operators in the Minkowski region. Okay, then this state won't necessarily be annihilated by the annihilation operators up in this region, because we'll have mixed them together. Okay, and this is Hawking's calculation, is to figure out the relationship between the creation and annihilation operators for modes down in the Minkowski region and for modes up in the Schwarzschild region, and then once you figure that out, in the vacuum, so now the state you pick is going to be the state where you don't throw anything in here. So maybe I should make that statement more ideologically. We want to know what the black hole is doing if we leave it to itself, right? So in the here we were sort of throwing stuff in and stuff was coming out, and the black hole was in part of an open system because we were constantly feeding it with more and more thermal radiation. But for an actual black hole, seems the simplest question is, okay, we make it and then we don't touch it. We just want to know what it's going to do. So what that means from the point of view of this diagram is that we want to start in a state which is annihilated by all of the annihilation operators down here. Because if it wasn't, then that would mean that there was stuff that we are throwing in here. But then what this argument is telling us is that that state will not be the ground state with respect to the creation and annihilation operators for these modes. Okay? These modes will be excited in the state where we didn't throw anything in from the beginning. All right, so now, unfortunately, so Hawking analyzed this problem in detail in his paper, and it's really a beautiful paper, and you should look at it. And if you find it cryptic, you should look at Wald's book, where he explains some more of the details. It's a little bit too much for me to try and go through all of the analysis on the board. Very roughly, the idea is you look at some wave packet here. You look at some mode that's sort of localized here. You trace it back. And then you argue that at sufficiently late times, this tracing back operation makes the packet sort of sharper and sharper, so that by the time you get to here, what's called geometric optics is a good approximation. Or in other words, that you can solve the wave equation by just pretending that you have a particle there, and that it's moving along a null geodesic. You then follow, so that the geometric optics then allows you to just pass through the shell, come back to here. So maybe I'll draw this. You have some mode here. You trace it back. It bounces off the origin of polar coordinates back down to here. And then you can figure out down here, you can re-express it in terms of the Minkowski modes. And that lets you work out the relationship between the two. Okay. But I'm not going to go through the details of that just because it would take another half hour. And it's easier to just tell you the answer. So what's the answer? The answer is that, so this analysis tells you that there's a flux of energy in each mode at infinity because of this mixing between the positive and negative frequencies. And the flux is something like this. So because omega is continuous, I actually have to tell you the flux in between omega and omega plus d omega because I'm eventually going to integrate over omega. So the flux in a particular mode is going to be proportional to the d omega, sort of some infinitesimal width. Times something called P absorb, where I'll tell you what that is in a sec. And then divided by some thermal looking factor. So now this beta is 1 over the Hawking temperature. Okay. And then what does this P absorb? So actually I should have just moved this back for a sec. So P absorb is the transmission probability. So this is being applied now to a particular one of these Schwarzschild modes, okay? Because we're computing the flux in the mode up here, so it's the Schwarzschild modes that are interesting. This P absorb is the probability if you send one of the modes in from the right that it transmits through the barrier, okay? So in the effective Schrodinger problem, it's the transmission coefficient. I don't know, I guess it depends. Maybe some people call it the square of the transmission coefficient. I can never keep track of this, but it's the probability of getting through the barrier. So now, first let's imagine that this wasn't here, okay? Now, you may or may not recognize the formula if this is not here. But in principle, if you have a good memory, you should recognize it. Because the formula without this P is the formula for emission from a black body, okay? It's the formula where you have some object sitting here, and it's at temperature and it's sitting in the vacuum, and this is some undergraduate statistical mechanics problem. And if you solve this problem, you'll find 1 over e to the beta omega minus 1 is the expected occupancy of a mode in a photon gas. And then, so since I'm computing an energy, I've got to put an omega there. So it's just the expected occupancy of the mode. Now, this P absorb is here because the black hole isn't actually a black body. A black body is defined as something that absorbs whatever you throw into it, okay? But we learned here that the black hole doesn't absorb everything that you throw into it because you can try to throw something in and it bounces back off of the barrier. So if you then go back and again do the undergraduate statistical mechanics problem, but now including that there's some probability for reflecting, you find exactly this formula. And you could have actually deduced this formula, and I was almost tempted to, just from this state. And the reason is that if it's possible for a black hole to be in thermal equilibrium with a photon gas outside that's at some finite temperature, and I argue that it is possible here, that's what's going on in this situation, then if you were to take that same object and put it not in the thermal bath, it has to emit like this. And the reason is because otherwise it couldn't be in thermal equilibrium. Otherwise I would just keep feeding stuff in, and it would just keep getting absorbed. And if it was never getting emitted, then the temperature would be just getting bigger and bigger and bigger. Well, actually, the energy would be getting bigger and bigger and bigger, which in this case means the temperature would be getting smaller and smaller and smaller. So you need to be able to emit just in order to be able to be in thermal equilibrium. Okay, yeah.
So is there a d omega on there?
No, because I wasn't sure exactly how to write this. What I want to write is the differential flux into the modes in the frequency range between omega and omega plus d omega. So yeah, this should really be the integral, the sum over all the modes is what this symbol sort of suggests. But I don't know. Maybe if I put something like this, omega Lm, that makes it more clear. And then to get the total flux, I'm going to sum over L and M and integrate over omega. Okay.
The sum radiation not necessarily only photon.
Right. So that's I was going to comment on that. So So for simplicity, the analysis I talked about here is just for a massless scalar field. There could be other massless particles around. Actually, in our world, we think there probably aren't massless scalar fields, but there are massless photons and massless gravitons. And you can do a similar analysis for those. It's a little bit harder because those fields have spin. The only thing that really changes is that because those fields have spin, so this P absorb, as we discussed, is clearly going to be smallest for L equals 0, because then the barrier is the lowest. And then it gets higher, as L gets higher. So then this thing at fixed omega is going to be a decreasing function of L. So then most of the emission is going to happen in the S wave, L equals 0, and maybe a little bit in L equals 1. Now, if we studied a particle with spin, then that couldn't be true, because you've got to conserve angular momentum. So if you just emit a spin particle from a Schwarzschild black hole and leave behind a Schwarzschild black hole, you violate angular momentum conservation, because now you've got this particle with the spin. So then the way that particles with spin decay is that they come out with some orbital angular momentum. They come out with some L, which cancels the angular momentum of their spin in such a way that the total angular momentum stays 0. So then they have to transmit into the higher L modes, which means they come out slower. So whatever the lowest spin particle around is going to be the one that dominates the emission process. So in our universe, that's probably going to be photons, because photons have spin 1, and the only other massless particles we know about are gravitons with spin 2. You can maybe talk, if they're actually massless neutrinos, then those are spin 1/2, and those would actually come out faster, I think, although I haven't completely worked it out myself. And that would certainly be unfortunate, because it's very hard to detect neutrinos. Well, it's hard to detect photons whose wavelength is 1 kilometer too. Yeah, that's really hard. Yeah, we hope it's photons.
Radiation does not have this scalar particle itself.
No. The electromagnetism, electromagnetic waves have polarization. They're either.
Somehow we didn't include electromagnetism here, but somehow we drive sort of electromagnetic contribution.
Well, no, we didn't derive. I started with a free scalar field, and I showed that in the presence of a free scalar field, you get some energy flux out at infinity. Now, if I included also the electromagnetic field, I would get more flux out at infinity. But that flux would be less than the flux in the scalar field because of what I just said about the spin.
That radiation also contains some information, or it's completely random.
We'll get back to that question. Okay. Yeah.
So where I see this fog picture that near the horizon has a pair of...
Yeah, so I had a rant about that in the notes. That picture was described by my advisor as a cartoon Hawking invented to explain his paper to children. Yeah, for kids. Right. Hawking radiation for kids. Yes. No, yeah, I don't like that picture. One serious problem with that picture is that the frequency of these modes are such that the wavelengths are typically of order the size of the black hole. So then it's kind of silly to talk about them as being localized particles. These S waves are very large. So
well, I mean, you can consider static observers close to the horizon when it's like the Rindler situation.
Yeah. So the people who are dangling down there, that picture is sort of more defensible. But I mean, my experience has been that this picture leads to more confusion than it removes. Yeah, it's better to just understand what's actually correct. Okay, so just a terminology thing. These absorption factors are often called gray body factors because, like I said, if this was 1, it would be a black body. Okay. Okay, so to summarize, we're led to the following picture of what happens with a black hole from collapse. So this analysis of Hawking was only valid for radiation that comes out sufficiently late after the shell collapses. So at first the shell goes in and there's some ring down period, where the black hole sort of is settling down into a quasi-stationary configuration. Once it's done doing that, then it just starts radiating like a gray body at temperature T. mostly into the low L modes because of these gray body factors. So any massless field that's around will participate in this. So most will be photons if we assume there aren't massless neutrinos, but there will be some smaller but order 1 fraction which comes out as gravitons. Okay, so that's the upshot of Hawking's really remarkable calculation.
Can I ask something?
Yeah.
When you say it's typical wavelength of Hawking radiation is on the order of a black hole,
Yeah.
but isn't that an observer-dependent statement? Because if I look from, for example, infinite near horizon, these modes will be infinitely redshifted or bullshifted or whatever.
Yeah. So I meant that comment mostly about the S wave. Yeah. But I mean, it's when you talk about particles, you really mean that you're in this sort of geometric optics limit where the compared to the radius of curvature of the geometry, the particle you just can make these tiny little wave packets that are scooting around, but you can't make the little wave packets. You can't make them smaller than the wavelength. Okay. Yeah.
So what role does the horizon play? Like maybe I got lost in the details.
Yeah. Well, yeah. So the thing is, yeah, it's sort of right. The horizon is important for why, for where this temperature comes from, right? Because it was in the vicinity of the horizon that the geometry was like Rindler. So then you had this business where sort of the space-time is sort of spreading near the horizon, and it's causing little fluctuations here to get amplified, sort of stretched, and eventually escape out to infinity.
Well, you implicitly use the large redshift when you get close to the horizon to justify the geometrical optics.
Yeah, that's correct. Yeah, that's correct.
Yeah, I also have a question. The thing is that from the point of view of someone outside the black hole, I mean, I've always had this picture that if I have a friend like falling down to the black hole and it's emitting signals, when it gets close to the horizon, the signals get very redshifted, so I would never see my friend falling down.
Yeah, that's
Here,
true.
I would get some finite frequency, let's say. So it doesn't know what is it? It is produced like just a little bit separated from the horizon.
Yeah, that's right. Because remember, the horizon is at r star equals minus infinity. So all these modes I'm talking about are outside the horizon.
So they are produced outside, and the other.
Yeah.
Let's say that the other part is.
Yeah, but I mean, you can sort of think about it. So if you imagine, a photon propagating back here, it looks like it's just running parallel to the horizon in the Penrose diagram, but the proper distance between these is getting closer and closer and closer. And that's exactly this redshift. It's sort of saying that from the point of view of some, of sort of the short distance physics going on near the horizon, if you zoom in here, this is somehow sort of coming out of very short distance fluctuations of the field, which are then getting stretched to macroscopic size. And that was this ideological comment I made at the beginning of the lectures, that somehow this property of horizons is what enables you to try and learn about Planckian physics, just by doing experiments, where the temperature is something like 10 to minus 6 Kelvin or something.
Within this picture of two particles that are on the horizon, is correct, yes, because as you said, it's come from this.
No, I think it's not correct. I think it sort of it has some flavor of what's actually going on, but I don't think you can think of as having localized particles here. They sort of are filling the whole near horizon region. I mean, if you could honestly, if you could have localized particles here, they wouldn't be created. I mean, the thing that enables you to have this business of sort of not seeing particles from one person's point of view, but seeing them from the other person's point of view, has exactly to do with the situation where the wavelengths of the particles is comparable to the radius of curvature, and then you can't really say what you mean by a particle locally. The particles are really only defined at past infinity and at future infinity, and then in between their waves. Yeah. That? Well, you mean, well, I'm not sure. I mean, it goes from r equals 1 to r equals infinity. R equals 1 is r star equals minus infinity. Oh, no, yeah, but distance in this graph is not proper distance. Yeah. I mean, the horizon, this is a finite distance to minus infinity.
Well, the interesting stuff is happening roughly a Schwarzschild radius away from the horizon.
Yeah, that's right. So, yeah, I mean, yeah. Well, yeah, that's sort of this whole region. Yeah, I mean, this is about a Schwarzschild radius. You know, well, it's 1/2 of a Schwarzschild radius away from the horizon. Okay. So now in the QFT in curved spacetime limit, which is what we've been working in so far, the mass of the black hole is infinite. So you may remember I said yesterday, the limit we're working in is I take g to 0 and m to infinity in such a way that I preserve the Schwarzschild radius. So in this limit, the black hole can emit a finite energy flux forever and never get smaller because it has infinite energy. So infinity minus the finite thing is still infinity. But that's obviously unphysical. Well, at least to me, it's obviously unphysical. I mean, that's just somehow there's some, I took some wrong order of limits in making that statement. Real black holes do have finite energy. And what that means is that this flux of energy out at infinity is eventually going to cause the black hole to start losing mass. Getting smaller. And if we wait long enough, well, it'll get very small, and maybe it'll get down to the Planck size, and then we'll have to think about what happens. So I'm going to postpone for a sec to think about what it happens part, and just try and get an estimate for how long it takes the black hole to evaporate. Okay, so I mean, the correct thing to do is to now get rid of my confusion with this formula by integrating it over omega and summing over L and M. So now this computes the real decay, the decrease in energy per time of the black hole. Okay. Now, unfortunately, these transmission coefficients are actually kind of hard to compute in general because you have to solve some messy differential equation to compute them. So yeah, Don Page did this numerically in his PhD thesis, I think, and so you can see the results online. And of course, by now, probably most of us could just do it ourselves. It's just a ODE. But for intuition, it's better, I think, to just I'll cheat a little bit and use the fact that I happen to know that in the limit where the frequency is small, I can approximately solve that equation. And you're just going to have to believe me because I'm not going to try and convince you. But I can solve it, and you can too if you stare at it long enough. So for omega sort of less than or equal to 1, P absorbed is something like omega squared. But now we get to something important, which is that so far, I should have made this comment at the beginning, now the black hole mass is decreasing in size. It's time dependent. And that means that even I am going to have to stop using units where 2gm is 1. Because it would be ridiculous to try and continue using those units when the mass is time dependent. So from now on, I'm going to have to start writing the Schwarzschild radius again. So it appears here, RS squared. Okay? Okay. Now, RS depends on the mass. So since I put a squiggly here, I'll just call it GM and forget about the 2. Now, the energy of the black hole, I guess actually I should put a minus sign here if I'm talking about this was the energy flux out at infinity. Well, let's see. Okay, no, I won't put it yet. So then the mass of the black hole is equal to its energy. That's not obvious, but it's true. I wrote some little rant in the notes about what does energy mean in general relativity. But if you go off to a mountaintop and contemplate that for a while, you'll come back convinced that the mass of the black hole is its energy. So then if energy is going out at this rate, then this gives us some differential equation for the mass, which is, let's see, I wrote it somewhere here. it's some minus, some constant c divided by gm squared. Okay. So in deriving this, I put this in here. I did the integral over omega. I used the fact that this p falls off at large L, so I just evaluated at L equals 0. Then you can do the integral by scaling. You get this result. So that's good. Even I can solve this differential equation. And maybe before I do, though, maybe I'll just comment. So as an intermediate step here, this actually, well, I'll just write it. This actually happens to be the area, which is something like g squared m squared, times the temperature to the fourth, with some number here, and this is what's called the Stefan-Boltzmann law. Okay, so the easy way to remember this is, rather than getting confused about gray body factors, to just say, well, I remember from my undergraduate physics class that a black body radiates with a flux which is t to the fourth per unit of area of the size, and then so this area here is right. It's the Schwarzschild radius squared. So this is the dummy way to remember it, and that gets the coefficient wrong, but I'm not going to care about the coefficient anyway. So that's the easy way to remember this. Okay. So okay, great. So I can solve this equation, and what I find is that the black hole evaporates in a time which is like g squared times the initial mass cubed. An easy way to remember this is it's just m cubed in Planck units.
Is the p going like omega squared valid in all dimensions?
No. But
What's the dimensionality dependent?
It's such that you get this in any dimension, but I don't remember exactly what the power is. Yeah, but you can solve the equation in any dimensionality. It's a different equation because the v of r changes in other dimensions. Okay, so this is a very long time actually, right? Because remember the mass of the black hole. So this is the mass of the black hole cubed in Planck units, and we'd already decided earlier that the mass of the black hole in Planck units was 10 to the 38 for a solar mass black hole, and now we're cubing it. Now we're cubing it and multiplying it by a Planck time, which is small, so it's not quite 10 to the 38 cubed, but still, if I take this to be a solar mass black hole, then this is something like 10 to the 66 years, which is a long time. So probably if we're going to try and test this, we're going to have black holes which are smaller than solar mass, which is a non-trivial statement because currently the only way that we know how to make black holes in nature is either by stellar collapse or by making a galaxy. Now, I'm not optimistic about making a galaxy either. So we're going to have to figure out some way, by scattering experiments, of making black holes efficiently if we ever want to test this. And well, I don't have any ideas. Yeah.
I'm not sure this question has physical meaning, but if I look at the pictures, we have stuff that we put inside the black hole, so inside the horizon, all these photons.
Yeah.
And then we have the stuff that is in the zone.
Uh-huh.
And it seems now that mass is getting out of what's inside, because some stuff is inside. And then it's out,
Inside means up here?
Yeah.
Yeah.
But it's still, it shouldn't get out, but somehow it does.
Yeah, so the way you should think about that, okay, so yeah, this is one of those things that's a little bit confusing, is that what's going on here is that there's an energy flux going out here, and there's a negative energy flux going in here. Now that may sound crazy to you, but in quantum field theory that's possible.
And if I would fall into the black hole and I would personally be in this top wedge, would I just get thinner? Or?
Well, no, so yeah, so let's think about time scales, right? So if you jump into the black hole in a proper time, which is of order m, because that, which is of order the Schwarzschild radius, you hit the singularity and die, okay? Now m, in Planck units, or it's gm, if I put the g back, is much smaller than m cubed in Planck units. So you die long before the black hole has a chance to lose any mass.
I wouldn't observe in any way.
No, you would not. Yeah.
So I'm a bit confused by your formula. P goes as right? Sorry, omega squared.
Well, I didn't derive
P
it.
is like 1 for like the black body for S wave, whereas
Yeah.
this seems to be dependent on the frequency of these things.
No, but that's because the thing is, for the black body, it's 1 for all the modes. So I did two things. I ignored all the higher L modes, and I replaced this by that.
Yeah.
And then the miracle is that those two things canceled to give me the black body formula. That didn't have to happen, but it did. Yeah.
But omega squared, just in the usual derivation of black body, is sort of the density of noise. It's not like in the black body. So there's somehow like this transmission probability is reproducing your density of states.
I'd have to go back and look at exactly what happens in the ordinary black body calculation, but I'm pretty sure that it's 1. And that if you interpret this correctly, this is 1, because there's no barrier. Stuff just goes in. Yeah. Yeah.
So this time is certainly much longer than the lifetime of the universe so far.
Yeah. So yeah.
So do you know what happens? So I mean, will this black hole also die because of the expansion of space?
Well, so far actually it's the other way. So yeah, so for me, black holes are laboratory experiments. So I make the space-time as large as I need to think about them. But if you want to put in cosmology, then already you have to worry about the fact that the cosmic microwave background has a temperature which is 3 Kelvin. Whereas for one of these solar mass guys, the black hole temperature is 10 to the minus 6 Kelvin, which means that a solar mass black hole isn't actually evaporating, it's growing, because it's absorbing CMB photons. So, we somehow have to, separate these things out. So, I mean, one way to do it is to just make the black hole smaller so that that's not true anymore. And I think probably if we ever do this, that's what we'll end up doing.
Or we can wait a long time for the black body radiation before.
Yeah, that's right. We can. Yeah, so that's the other thing we can do is we can wait a few billion years. Yeah. Yeah.
EM over dt, this formula actually based on the quantum field theory.
Well, no, I've gone beyond quantum field theory here, because remember, in quantum field theory, m is infinite. So now I'm making a physical argument here. I'm saying that if I back off, if I let G Newton not be 0, then also m no longer has to be infinity. And then if I believe in energy conservation, which I do, then some formula like this has to be true. So that's it. Okay, so now I want to. So now we've derived Hawking's result. Black holes evaporate. That's great. So now let's think a little bit more about what that actually means. Here we go. Okay. So believe it or not, we're done with quantum field theory, we're done with modes, and we're done with coordinate transformations. But I don't know. It's good to see these things once, I guess, at least. Okay, so now we've decided that a black hole has an energy, and we've decided that it has a temperature. Once that's true, then, well, it means that it's probably also got an entropy. One way to think about that is to just observe that the usual definition of temperature is that. Okay, that's the statistical mechanics definition of temperature. If, in particular, say that I had a formula for temperature as a function of energy. Say that someone just happened to hand me a formula for temperature as a function of energy. Well, probably, the second thing, maybe the first thing I would do with it, I don't know, is that I would then try and integrate it to find the entropy. Okay? So we can do that here. So remember, T is 1 over 8 pi g m. And m is E, or E is m. So we can compute ds dE as a function of E. We can integrate it. And if we assume that S of E equals 0 is 0, so that there's no entropy if there's no black hole, which doesn't sound crazy to me at least, then we find that S is the area of the horizon. So that's 4 pi times rs squared, divided by 4 times g. Okay? And this is, we're to interpret as the entropy of the black hole. Now, this is a little bit confusing because in classical general relativity, black holes don't have entropies. There's really not much to black holes. You know, they've got a mass, maybe they've got a charge, maybe they've got an angular momentum. But that's basically it, okay? And this is large. I mean, this is 2 pi, so in my units, it's 2 pi times the area over L Planck squared, okay? So the Planck scale is incredibly small. So for any black hole that we know about, this is incredibly large. I think I computed for the solar mass black hole, it's something like 10 to the 78. This entropy is 10 to the 78. Well, how do we make contact with this? So, okay, here it's good that Jacob is in the audience. So Jacob was the first person to really think about this, and he argued that this really is the entropy. So of course, actually, he's a smart guy. So he argued this before he knew about the temperature, via interesting chain of arguments, which I'll maybe briefly summarize in a sec. But for now, let's pretend that he came up with it this way, just for the pedagogical flow. He said that this entropy is really counting the microstates. It's counting the number of different ways that you could have made the black hole. And that's really a remarkable claim. I mean, I think it's a very physical claim, because the classical black holes are really strange. You can make them by collapsing all different kinds of things, and in the end, you just always get back to the same geometry. It's sort of very, I don't know, disturbing. So maybe I'll just briefly comment on the way that Jacob came up with this. So there's a classical theorem in general relativity that the area of horizons always increases. Okay, even if you throw stuff into the black hole, you collide black holes together. When you're done doing whatever it is that you did, you find that the sum of the area of all the horizons is always increased. So this sounds like a lot like the second law of thermodynamics, and you might be inclined to think that some multiple of the area of the black hole is like its entropy. So yeah, Jacob also actually found that even though he didn't know this calculation of the temperature, you can just guess that maybe there's a temperature, and you can figure out what it is by saying you know that the energy is the mass, and you know that the entropy is the area, and then so you find some temperature. So you don't get the coefficient, but you find that it's proportional to this. So and it has nice properties, like it's positive. That's a good thing for a temperature to be. And he was actually able to, then consider a whole bunch of fun thought experiments of, throwing various classical and quantum mechanical systems, so beyond just the classical relativistic things, but really throwing quantum mechanical entropy into the black hole. And whenever he did it, he would always find that the total entropy would increase, So if you take some entropic system and you throw it into the black hole, the entropy of the outside has decreased because the system isn't there anymore. But the black hole absorbed it and its area increased. And Jacob was able to argue that the increase of the area is always bigger than the decrease of the entropy outside. So that he called the generalized second law. Now, I had a slightly snarky comment here. I guess if you really take his argument that this is actually the entropy, then there's nothing generalized about it. It's just the second law. Entropy increases. So the real statement is that this is indeed entropy.
Maybe I comment on this.
Yeah. Please.
The ordinary second law in this context is if you take an hypersurface, a Cauchy hypersurface, which is sort of space like outside the black hole, goes inside the black hole, then on a series of such surfaces, the total ordinary entropy should increase. That's just from local dynamics. That's the ordinary second law.
Well, that's sort of the relativist
What
second
we
law.
say here
Yeah.
is something else. Sum of two observed quantities from the outside
Yeah.
always increases. It's not the same statement.
Yeah. Well, okay. If you yeah, you could say that this is the second law from the point of view of somebody outside. Yeah. Yeah. Okay. All right. So great. That's fun. I should say that because of the discussion we just had, this entropy is usually called the Bekenstein-Hawking entropy. So just to be clear, Jacob figured out that this should be the entropy, and Hawking computed the prefactor by figuring out what the temperature is. Okay, so on to the information problem. This suggestion that we should think of this as really counting quantum microstates, it seems irresistible. But Hawking managed to really cause some trouble by arguing that if we actually take that seriously, if we actually say that this is the entropy of the black hole, that this is inconsistent with quantum mechanics. So that's bad, and we need to understand that. So the argument is very simple. So you just imagine you start with a black hole that you formed in some pure quantum state, psi. Okay? The pure state could be just some shell of photons in a definite configuration. So as time goes on, this radiation starts happening. Well, I guess it's not actually this radiation. It's the radiation that's behind it starts happening. And I didn't show it to you explicitly here, but if you look at the quantum state of the radiation, so here I just wrote the flux at infinity, but if you write down the quantum state, you find that there's absolutely no correlation between the different modes. Each mode is just is sort of thermally excited, including one of these absorption probabilities. So there's some paper by Wald that makes that very explicit. So the entropy is just coming out in a mixed state, and the energy is coming out in a mixed state. It starts out not being very mixed because only a few photons have come out, but then as it's coming out, it's getting more and more mixed. Without limit, actually. So Hawking says that in this situation, if we plot sort of the entropy of the radiation field, the von Neumann entropy, as a function of time, it starts out 0 because no radiation has come out yet, and then it just increases. Okay, that's the von Neumann entropy. And it keeps going as long as this calculation is valid. It should keep going. Now, we argued that the validity of this calculation is based on this ratio, m Planck over the mass, being much less than 1. So as long as that's the case, this entropy keeps increasing, which means that, we keep going until we get to the point where the black hole is Planckian. Okay, and now we don't know what happens. So Hawking suggested two options for what might happen at that point. Let's see. Maybe can get rid of the two-sided black hole now. So option number one, is that the evaporation stops. This is called the remnant idea. So it just it keeps shrinking, and then you get down until you have just some object which is Planckian size, and it's just sitting there. And then the calculation breaks down, so we don't know what happens. But one thing that could happen is it just sits there forever. Okay. Now, I have to add a constant. Oh, you mean to this? You yeah, that's what I was. Yeah, that's what I was about to say. So,
it can also be finite.
No, it can't be finite because the thing is, you can start with an arbitrarily large black hole, and if the larger of a black hole you start with, the more of this you get before you get to the black hole being Planckian size. And then if you want to save quantum mechanics, if you want to have the final state be pure, then all of this entropy up here in the radiation field has to be entanglement entropy. And the whole radiation cloud with arbitrarily large amount of entropy has to be purified by this puny little Planckian size system which is sitting there. Okay? So this system, there must exist in nature for this possibility to be true, Planckian sized objects with arbitrarily large entropy. Okay? I don't like this. I think it's silly. Now you could say that the other options are also unpleasant, but this one really seems ridiculous to me. I would say if you believe in this, it's essentially killed by ADS-CFT, which I may say a little about tomorrow. That's it is an option, and I can't really rule it out. Hawking had an argument based on CPT against it, where he said, well, if you can make a black hole just out of photons, then it should be possible for a black hole to decay just into photons, since the laws of physics should be CPT invariant. So then it would be a little weird to have things which, the black hole, it can't quite make it all the way back into photons. It's not a completely convincing argument, but I think it's worth thinking about. Okay, so option number 2 is that the evaporation finishes, and then quantum mechanics is wrong. Okay, and this is Hawking's position. Okay, so the thing is, it is as of 1976. Yeah, that's right. It's well. So why does quantum mechanics have to be violated? Well, the thing is, the remnant. By the time the black hole gets down to Planckian size, it really doesn't have very much energy left. And so if it just explodes into photons, that process has got to conserve energy. So then the photons that you get out of that final explosion have some energy which is not that big. And that puts a limit on how much entropy they can carry. And in particular, they can't carry nearly enough entropy to purify arbitrarily large, the arbitrarily large, rest of the radiation, which has already come out. So if you think the evaporation finishes, and you think that this description of the quantum state of the evaporation is correct, then you've accepted that quantum mechanics is wrong, because we've constructed an isolated system where a pure state evolves to a mixed state. Okay? And that's terrible. Yeah? Well, I chose to make it pure. You can't stop me. I started in a pure state. Well, I don't know. No, I mean, I think we can prepare pure states, right? We do some measurements and make pure states. Yeah, I think if we're doing quantum mechanics, we've got to be allowed to think about being in a pure state. No, it's not. It's just the state of the initial radiation field. I just want the initial shell to be in a pure state. There could be something else going on over here. We could be, over here having tea or something, and that doesn't matter. I mean, it's just the initial state of the collapsed matter has to be pure. Yeah.
What I'm thinking about is, when you get to the Planck scale, the quantum effects should be already large compared to the scales of your mass of your black hole. So your Schwarzschild, the assumption that you have a completely isotropic system shouldn't be valid. So why do you assume that Schwarzschild
well, so until I get down to it being Planck size, it will be spherically symmetric, because the dominant decay is into S waves, and that preserves spherical symmetry. And even actually the decays into the higher L will have to preserve angular momentum, so they'll have to come out in some superposition of different m's, such that the whole thing stays rotationally invariant. Yeah.
Apparently, this thermal radiation which you get out, people try to find correlations between them, but they fail. Is it possible to see it with the calculations of each one?
Yeah, so that was the words I said over here. So if I had done for you Hawking's calculation, and actually I had done it slightly more carefully like Wald did, then I would have convinced you that the quantum state that comes out here is a mixed state, where it's a product over each of the modes times some thing that almost looks like a Boltzmann distribution, but is weighted by this absorption probability. Okay, and that calculation is supposed to be correct to leading order in this. Okay. Now, okay, that said, obviously, I mean, I don't like either of these two options, right? So, I'm willing to stretch a bit to try to avoid them, okay? And so is everybody else, I think, certainly in this field. So there's a secret option, option 3, which is that Hawking was wrong. Okay, but so there's various schools of thought about this. I mean, he could have just been completely wrong, and the black hole doesn't evaporate at all. He could have been, now that I think would also be outrageous because, this calculation is based on understood physics. It's based on assuming that quantum field theory in curved space-time is correct when you're at distance scales which are large compared to the Planck scale. And if that were false, that would also be a disaster, right? I mean, then we would have to understand why doesn't that happen all the time? I mean, it's all of our understanding of physics is based on this idea that short distance physics doesn't really affect too much long distance physics, right? This is the renormalization group, and I mean, that's really all that went into assuming that you're allowed to use quantum field theory to compute what's going on here. So it better not be completely wrong, or at least that's my feeling. But then there's a 3 prime, a little bit. Now, the little bit can't be too small. I mean, if it was this small in the quantum state, that wouldn't help. You can't turn a mixed state into a pure state by just adding a tiny little quantum correction. Okay, so it's a little bit, but not too little of a bit. So the idea is that the information gets out in subtle correlations. Okay. So that the radiation, if you don't look too hard at it, it looks like Hawking was right. It looks like it's just coming out thermally. But if you're smart and capable, and you take the radiation and you stick it into your favorite quantum computer, which you happen to have lying around, then you can figure out that it's not in a mixed state and that it's in a pure state, and you can do interference experiments, and but you have to do quantum operations on some order 1 fraction of all of the Hawking radiation before you start figuring out that the state is pure. Okay. Now that's actually very plausible because we think that's probably true for the gas in this room, right? Also, I mean it's probably not in a pure state. I mean the window is open and the door is open, but it's also probably not exactly in the canonical density matrix. And we can, if we look at all the particles very carefully, we can figure that out. We can figure out what the state actually is. Okay, so I think most people would have gone with this option, especially recently, after people came up with exact quantum theories of gravity, where it's sort of manifestly clear that this is what happens.
When you say most people, 20 years ago, it actually broke down on purely partisan ideological lines.
Yeah.
That is, the general relativists had no reason to believe in unitarity, and the field theorists had every reason to believe in unitarity.
Well, yeah, but I mean, stuff has happened since then, right? I mean, yeah.
Since we're talking about 1976.
Yeah, so in 1976, I think actually, well, maybe even this was the most popular option. I mean, I guess, well, at that point, the only people who were thinking about this were relativists. And, if you're a relativist, you're going to listen to Hawking, right? So, well, unless you're Jacob. But he was right, so that's okay. Okay, so why did, so other than the fact that aesthetically this seems nice, but I mean, again, I should comment that even effective field theory being a little bit wrong is already kind of a big deal, right? I mean, it's still a breakdown of the renormalization group, and it's not something that we should just give away without feeling the pain of giving it away. I mean, this really is, the more you think about this option, the more you realize that it's also radical. Okay, it's not just obvious that this is correct. So what convinced people that it is correct? Oh, so yeah, actually, John, how do you feel about giving me like till 45? Is that okay, or should I? Okay.
You're just getting started.
Yeah, well, you know. 3:45, 8:45. Yeah, I go all day, man. All right. Yeah. So good. So yeah, maybe let me make first a comment about why you might think that a breakdown of effective field theory here might actually be okay. Okay. And it has to do with the comment that I was making before. So if you look at what these modes are doing, so remember in these tortoise kind of coordinates where the potential is like that, right? So we can imagine projecting onto some wave packet that's coming out here at late times. If you follow this wave packet backwards in time to try and figure out what it was doing back when it was near the horizon, well, here's what happens. You'll follow it back, and there, some part of it will bounce off of the barrier and go back out and won't make it in. So there'll be a you take a wave packet going out here. You trace it back. Some part of it will bounce off like that, but some other part will be transmitted through. Okay, so transmitted through going backwards in time. And if we look at what is this part doing, well, it's just some wave packet here, and it's propagating back in the tortoise coordinate. Okay, but that's actually a little bit confusing because remember I said before that r star equals minus infinity is only a finite distance away from the barrier. So as this wave packet propagates back further and further in time, it's getting squished into a smaller and smaller physical proper size. Okay, so it's coming out of a region which at some point is only a Planckian distance away from the horizon. Okay. Now, what Hawking's calculation actually does is he says, okay, that's fine. Even though it's Planckian size, I'm still just going to trace it back. Trace it back through the infalling shell, and then bounce it back and down to, well, I probably shouldn't do that, down to t equals minus infinity here in the Minkowski region. And it actually so happens that for the wave packets that come out late, the frequencies of the modes that they mix with down here are arbitrarily large. The later the mode comes out, the higher the energy of the mode here. Okay? And in particular, this collision with the infalling shell that I sort of hand-waved away, mumbling about geometric optics, if you actually look at the S, well, that's particle physics language, but you look at the center of mass collision, energy of the collision between this wave packet as you trace it back and the shell, it's higher than the Planck energy. Okay? And when does that happen? Well, it happens if you look at modes that come out in a time after the shell, which is the Schwarzschild radius times the log of the Schwarzschild radius over the Planck scale. Okay, that's just some statement about figuring out in Schwarzschild time how long does it take this thing to get back to being within a Planckian distance of the horizon. So this time has a name. It's called the scrambling time. It's appeared in various contexts. I guess actually the people who really beat it into us that this is a time you should think about are Patrick and John. But I think in this context you should think of it as if you ask about modes that came out more than this time, and notice this time does go to infinity as L Planck goes to 0. So this time would not have existed in the quantum field theory and curved space-time analysis. Then you might be a little bit suspicious about continuing to exactly believe Hawking's calculation. So this is called the Transplanckian problem. And some people try and there are various arguments about whether or not the Transplanckian problem is serious. There's something called the nice slice argument, which is supposed to make it so you don't have to worry about the Transplanckian problem. But I should say I don't really find it completely convincing. I think that this may indeed be a good reason why you should trust Hawking's argument only for times exactly only for times which are smaller than the scrambling time, and that something interesting might start getting into the radiation after this time, because there it's sort of we're not really violating decoupling because indeed something is becoming Planckian. And so I think this intuition was part of why people were sort of willing to take this option more seriously.
Why do you say the nice slices argument is not like
Um,
not completely right?
Yeah,
Because the same problem would happen in cosmology, right?
Oh, yeah. That's right. Let's be careful. So when I say that, I didn't say. So one thing I could conclude from this is that after this time, Hawking is totally wrong, and maybe the black hole explodes. Maybe just now I don't actually know without having a theory of quantum gravity, but I think the sort of the validity of this up until the scrambling time sort of suggests to me that it's sort of getting the coarse-grained features right. So that if I tried to apply it at some later time, I would also, over sort of short times, see that the radiation basically looks thermal. And it's only if I try and apply it to all the radiation that has come out at once that I can start getting into trouble. So in cosmology, we're only ever looking at the coarse-grained, features of the fluctuations. We're not trying to feed the CMB through a quantum computer and decode some interesting quantum information. I think actually we wouldn't be able to even if we tried because the physics of the problem is different. So, I'm not saying that because of the trans-Planckian problem you can't believe in inflation or you can't believe in even the coarse-grained features of Hawking radiation. I suspect you still can. But I've never seen a good argument that it can't lead to some sort of subtle modifications of the type you would need to get information out. Okay, but this unlike other things I've said, this is my view and not universally shared. Yeah.
So for the non-specialist, like basically you draw one photon, but there are many of them coming out at different times. So where is the ones that are?
Yeah. So I picked a particular wave packet. There's other wave packets coming out too, but I just wanted to.
Trying to say that there are a few wave packets that came out before this time.
Yeah, there's some coming before, there's some coming after.
This time, how does it compare to anything else? It's much smaller than the lifetime. So
Yeah, it's much smaller than the lifetime. It's much bigger than the Schwarzschild, than the light crossing time, the Schwarzschild time. So it's just some intermediate time scale. It's a new time scale.
most of the photons comes out after.
Yeah, that's right. Most come out after. Yeah, most come out after. Okay, great. So let's see. So yeah, now I just wanted to make a few sort of, so from now on, I'm going to take this as an excuse to assume that the evaporation is unitary, okay? Now, a better excuse, if you don't find this convincing, is that there exists actual models of quantum gravity. Two I'll mention are the BFSS matrix model. That's Banks, Fischler, Schenker, and Suskind, and the ADS CFT, where you can just sort of explicitly see that you can describe the formation and evaporation of black holes in a manner that's unitary. And I think that's what really settled the debate. But I think it's, well, it settled the debate in the sense of knowing that option 3 is correct. But it didn't settle it in terms of knowing why or how Hawking was a little bit wrong. And I think that also needs to be understood. And I think probably this observation is going in that direction, but certainly it's by itself is not explaining it. Okay, so that said, okay, great, the evaporation is unitary. So I think I'll close with just one final comment about what that actually means. So I said way back in the first lecture that in Minkowski space, the right way to describe physics is in terms of an S matrix. Okay. You might have said, why didn't I, S matrix? It seems like I'm throwing away information. So the S matrix is, just to give you some sense of what the S matrix description means. It says, you throw in some stuff from past infinity. So some of it can be massive, and then something happens, which you don't try and keep track of. You don't try and go see explicitly what happens, and then some stuff comes out, okay, and some massive stuff could have come out, And then what you want is you want the probability of seeing some final state chi, given that you had some initial state psi. And this is obtained from the action of a linear operator, S, which maps initial states to final states squared. It's a 2. Okay, so that's the S matrix. And you might say, well, I'm throwing away information, that all of this stuff could have been gone knowing, I'm restricting myself by only asking about this. But actually, once we turn G Newton back on, we stop taking G to 0, then there's a fairly, I think, compelling argument that this is actually the only thing that really can be well defined. In particular, we shouldn't talk about the kind of things we like to talk about in quantum field theory, like correlation functions of local fields at various points in the geometry. And the reason is physical. It's that gravity is universal. Once you turn on G, everything sources the metric. So say that you want to locate some point where you're going to put a field. Well, how are you going to locate the point? You're going to have to do it by some construction with clocks and rods, so that you can give some physical meaning to what that point is. Okay, but those clocks and rods are going to be heavy, and they're going to change the geometry. And so there's not really a way to just say what the point would. You can't really use the clocks and rods to say sort of what the point would have been if the clocks and rods weren't actually there. That's not an operational definition. So the only thing which you can really operationally define is this kind of thing of stuff going in and stuff going out.
The asymptotically flat case?
Yeah, the asymptotically flat case. Yeah, that's right. Yeah. In ADS, it'll be a similar but different story. Okay. And intuitively, you can just think of this S as e to the minus infinity times the Hamiltonian. Although obviously you have to take any expression like that with a grain of salt. Okay. Now, I think the point I'll close with is that in order for the S matrix to have any non-trivial content, I have to have some description of what the states that go in are and the states that go out. Okay. And here the intuition is that this business of stuff interacting gravitationally is actually not so bad as you get out near the boundary. If you imagine, throwing in some particles, if you pull them out sort of arbitrarily far away from each other, then they won't actually gravitationally interact. And so that on this slice only, you may actually be able to label states as if you were just in free quantum field theory, okay? In the sense of you have some non-interacting particles going in here, and all you have to say is sort of how many particles are there of such and such type, such and such momentum, such and such spin. So you just specify that here where they're so far away from each other that they can't interact. You send them in, whatever happens, they lose their identities, they mix with other things, they become non-local. But then something comes out, and then for what comes out, you can say the same. So then the idea is that the sort of labels on the S matrix, the indices, are just those of some free quantum field theory in Minkowski space. So in particular, it makes sense to talk about the S matrix for sending in a shell of photons and getting out some shell of photons, or some state of photons, which is the kind of S matrix element we want to study in doing black hole physics. Now I should comment that intuitive argument also is confirmed in the BFSS model. So this one isn't in asymptotically flat space, but this is, and you can see in the matrix model explicitly how you can construct, for example, the S matrix of gravitons. Now I guess it's the S matrix of gravitons in 11-dimensional supergravity, but you take what you can get.
Do they construct it?
Yes, yeah. They can't necessarily compute it, but they can construct it. They can write down the formula for it in terms of some unitary quantum mechanics. Okay, so I think I'll stop there, and then tomorrow I'll say a little bit more